All right, everybody, welcome back. We are at 12:30, and we're going to go ahead and start the attachment presentation with Rob McDonald. So with that, Rob, by all means, take it away.
Thank you very much, Brandon. As Brandon said, I'm Rob McDonald. This presentation has a lot to it, and we'll start with a bunch of slides that I hope will make everything clear. And if we have enough time, we'll try and do a quick live demo that will demonstrate a bunch of these features. And this is sort of a grab bag of features that allow you to better set up your models to capture the designer's intent, and that allow you to organize your models in better ways. And so we'll be talking about attachment, hinges, symmetry, sets, and subsurfaces. So without further ado, each component in OpenVSP is placed in the world based on its attachment point. And so what you'll see when you add a component, there's the global orientation shown down in the corner. And anytime we show one of these orientation triads, we use the colors red, green, blue to represent X, Y, Z in that order. So even though it's not labeled, this dash triad, you see red, green, blue, you know that's the X, Y, Z location. In this case, this pod is positioned relative to its attachment point. And when you position a point with a relative button, that's what it's saying. We are 2 units in the X and 2 units in the Z relative to its attachment point. Normally, of course, the default is 0, 0. So when a component gets added, its attachment point is drawn right at its nose. And then what you can do is move a point relative to its attachment point. And then, of course, attachment allows you to move where the attachment point is. When you place components in the tree, in the Geom browser tree, what you'll see is you can place them in a hierarchy. So you can make a component a child of another component. And when you do that, you then have the option of attaching it to a parent. You don't have to. You can just use the tree for organization, but you can also use the tree for attachment. And so you can only attach to a parent. And when you do that, you'll notice that there's a little caret that gets displayed. So the second pod is attached to this parent pod. And in this case, what we have is the green pod, which is the one that's selected, is attached to the gray pod. And so we notice the green pod's attachment point is located right here. And we've done this because you'll notice in the attached to parent section down here of the transform tab, it has been attached in both translations and rotations to the parent's component coordinate system. Your choices here are none, don't attach it to the component coordinate system, or attach it to UW. We'll talk a little bit more about what that means in a moment. But so we've attached, and then you can separately choose to attach translations and rotations. In this case, both are attached to the component system, and then it's moved relative to that to 2 relative to that. So that's why it's not located at its dashed triad. You'll notice its absolute coordinates then are actually at 4, 4, and that's because this gray pod was located 2, 2 away from the origin. So 2, 2 away from the origin, 2, 2 to the from the attachment point locates this green pod at 4, 4. When you attach any UV coordinates, what you're actually doing is you're placing the attachment triad somewhere on the surface of the parent. So instead of it being measured relative to the parent origin, which is at typically the nose of each component, the UV coordinates run from 0 to 1 along the surface. So U and V, one of them runs from U, in this case, runs from nose to tail. And so you can see we're basically 5% along the length. And W runs circumferentially all the way around from 0 to 1. So here we are 90% of the way around, and it looks like it's going counterclockwise. So at 90% of the way around, we're almost back to the beginning. So we're almost back to the top. I think that's the right orientation. And since we've both translated and rotated, you'll notice that this UV coordinate system is tangential to the surface, with the X direction running in U, the green, the Y direction running in W, and blue, the Z direction running normal to the surface. So what we have is we're slightly offset from the nose in this coordinate system, and then the green is 2, 2 in XZ off of that. And that's why you notice that the absolute coordinate ends up with these odd values, and it's because of this rotation from this point. But you can use attachment to attach to the surface or just the origin of an apparent component. Now, there's relative and absolute as a choice in what you do. And this can be a little bit tricky because when you're not on this tab, if you move a parent component, no matter whether it's relative or absolute, if you've used attachment, it's going to move. The attached component always moves when the parent moves. But what this does is it allows you to type in the value in a relative sense or an absolute sense. For example, and usually you'll use relative here, but and so you'll set the attachment point like we said, and then you'll set the relative offset. But occasionally you may know that you want to attach something either in component or UW way, but then you also know from, say, another 3D model, a set of drawings, or something else, you know what you want the absolute orientation and position to be. So what you can do is you can set that attachment, change it to absolute mode, type in the exact values of the XYZ and the rotations that you want, and we will actually back solve for the relative required to do that. And so what this actually does, it should be pretty simple, and it is when you get used to it, but it actually allows you to do some very powerful things by changing between absolute and relative as you move along in a model. So there becomes sort of a hysteresis here, and you can change the structure of a model, change the parent-child relationships, move components around by switching them, say, to absolute, turning off the parent-child, moving what it's a parent or a child to around in a model, reattaching it, and then setting it back to relative again. And that'll become more clear when you play with it or when I do the demo. There's a special kind of component in OpenVSP called a blank, and there's no actual geometry to a blank, but what a blank is really useful for is inserting its own coordinate system. So if you want a part or a component coordinate system, you can name that blank, use it to group components, and attach things to them, and it will build up and show you that for that blank. And you can also use it for a point mass and mass properties. And when you draw a blank, when a blank is visualized, the attachment point again is shown with the dashed triad, but then the blank itself is shown as a little red dot with a solid line triad so that you know where the blank component is and what its orientation is. Somewhat more complex, but in a similar vein, there's also a hinge component, which can also be used as a one-dimensional linear slider. And if you want to build any sort of articulation into your model, whether it's a tilt wing, moving landing gear, folding wing, anything like that, you'll want to use a hinge to do that, or a slider. And so you can add simple motion, and a hinge is kind of like a blank in that there's no geometry. It's just used for coordinate system building up. But there's a few things that are different. First, notice that a hinge, there's a double arrow. And what that means is the hinge forces all children to always be attached to the parent. It just doesn't make sense to have a hinge where the children are not attached. So that gets forced, and the double arrow represents that forcing. When you're thinking about a hinge, you need to think about a fixed side of the hinge and a motion side of a hinge. And I like to think about this in terms of the hinge on your door of your house. The door of your house, one side of the hinge is screwed into your house, the door frame, and that is the fixed side. And of course, the other side of the hinge, the one attached to the door, is the side that actually moves. So that's the motion side of the hinge. And in the hinge component, what you have to do first is you specify the fixed side. So it can be attached to its parent and moved relative to that and get its orientation. And then you specify the position and orientation of the hinge. So that's the rotation axis and where it starts. And that's specifying the fixed side. And then the motion side is then either rotated or if there's a slider, translated relative to that. And you'll notice in this, the attachment point is this long dashed line. The hinge fixed side is a solid line. And then the short dashed line is actually the motion side of the hinge in its moved point. When you're setting up motion control, we default to a hinge, and there's you can control the rotation, the translation of similar controls. There's the ability to set the minimum and the maximum angle for the rotation to go to. That way you can build that knowledge in your model into the VSP model. And you can then change the rotation between those stops very easily. There's also the rotate slider, which actually controls the current angle. You can turn on or off these limits by hitting these buttons so that you can, if you don't want there to be a minimum angle, you can turn it off. There's also this set button, which if you dial in the rotation, let's say you dial this into 22.86 degrees and you decide that looks really good and you want that to be your minimum angle, whatever it's set to, if you then click the set button next to min, it'll assign that value to the minimum. And likewise, if you then move it up to 64.3, you decide that's the maximum angle, click the set button and it will set the maximum to match that. So you can set those. And then this range button, what that does is it sets the range of the slider to match the min and the max, so that when you move the slider all the way to the left, it corresponds to the minimum value. And when you move the slider all the way to the right, it corresponds to the maximum value. So using these buttons, you can sort of tailor the operation of these motion sliders. There's a lot of ways to specify the hinge orientation. If you just think about a vector in 3D space, you can specify that vector through a set of Euler angles. You can specify it through XYZ components. You can specify it as starting at one point and ending at another point. You can specify it based on a normal vector to a surface, etc., etc., etc. And so VSP, the hinge, allows you all of that control, and it gets a bit confusing, but this input allows you to basically, if you want to use just angles from the Xform tab, you click rotations here at the top, and it uses the Xform tab just as any other component. Otherwise, if you want to use this tab, which is a little more complex, you choose the vectors button, and it uses this GUI to specify the angle. This vectors section tells you which axis you want to rotate about. Do you want to rotate about the X, the Y, or the Z? And the reference tells which direction the minimum and maximum angle are measured relative to. So the 0 direction, in this case, we're going to be rotating about the X in the triad with our angles measured from the Y. And so that's always, and these are grayed out because you can only choose different choices. So this axis and reference will always be shown, but down here will be the different options for how to specify the vector. So you can either do a 3D vector, you can choose a point in 3D, you can choose a point on another surface, or you can choose the U, W, or normal direction from another surface. And all these options allow you to choose what is that other surface that it's normal to, an offset from it, an XYZ point, start and end, the UV, etc., how to do that. Here's an example of a hinge, and I'll do this live when we have a little bit of time for the demo in a moment. But I've got this example where first we have a simple hinge at the tip, where you can see the rotation is sort of aligned with this chord. And so the tip folds in, and it's set up to fold all the way over, and its position is actually aligned with the top surface of the core of the airfoil. So you'll notice it's a little bit offset here. So it folds over until the wing folds flat on top. And then this also has a Grumman fold. So this hinge axis is 45 degrees in and down at about the quarter chord in the center. And that causes this wing leading edge to fold down under until it's back parallel to the fuselage. And so this is a wing with two folds. First the tips fold, then the rest of the wing does a Grumman fold back along the body. I'll show you this demo in a minute. Symmetry is another great way to build design intent into a model, and components have many options for single symmetry. So we don't really support multi-symmetry, or at least symmetry about multiple origins, but you can have multiple kinds of symmetry about a single origin. And so each component that you want to be symmetrical, you need to think about, is it going to be symmetrical about its own origin, its parent's origin, its grandparent, how far back of an ancestor, or all the way back to the global ancestor's origin. And then it can be either planar symmetry or axial symmetry, where you specify the XYZ axis and then how many rotations to make it like a flower petal. The origin is chosen so that you choose itself, in this case, a power face. It can be about itself, which is going to be 1. Me, myself, I'm 1. My parent is 2. My grandparent is 3. My great-grandparent is 4. So you go up the hierarchy that way. The global origin is always a choice, and it's always 0. So you can choose that as what you have your ancestor symmetry about. And then, of course, each of these levels, for example, the pylon, it has its attachment point and also the object itself, its own coordinate system. And so you can choose, do you want to be symmetric about each component's attachment point or its own origin? And you can use that to build up any level of symmetry you want. Changing gears a little bit, sets are a really important thing to learn as you're using VSP to do engineering analysis. So you're not just building a pretty 3D model, but you're doing something with that model, some sort of analysis. So sets are a way of organizing a model by purpose. So instead of it being a hierarchy by geometry, we're now going to organize components by what you're going to do with them. And one of the ideas of this is not all the components are needed all the time. The outer mold line, the OML, is needed for aerodynamics, but if you have a passenger inside or radio or an engine represented internal to the airplane, then you don't need to represent that in the OML set. And so since you're doing different purposes, when you're doing aerodynamics, you need one set of components. But if you're doing mass properties, then you may need the equipment and the payload and those things that are internal. Different sets for different purposes. Any geom can be a member of more than one set. Sets get names, so you can name it by that purpose. You can call one the aerodynamics set and another one the mass properties set. And then actions, think of this as a verb. You do things to sets. You take an action on that set. Sets show up all over in VSP. They're pervasive, and you can use them all over the place. Any analysis you do in VSP, you're going to have a little pull down to tell it which set you want to do that analysis on. Every export option, there's going to be a set. And if you're using the API, you're going to specify which set you want to act on all over the place. Another trick thing to do with sets is you can have what I call pseudo-duplicate components. You can have two versions, Dr. Jekyll and a Mr. Hyde, of certain components, and then they can be in different sets. So for example, you might have your real wing in one set, but you might carry a simplified reference wing in a different set. And that includes different, a simplification of that plan form and other things like that. In general, sets are a power feature. This is an advanced thing, but if you're using your models to do calculations, you're going to find that you absolutely love sets. Once you understand them and use them, you won't ever go back. You won't know how you ever worked without them. They're really key to being a power user with VSP for analysis. I'll give a little bit more detail on sets. You can pick which sets a geom is in right from the geom editing window. So for example, in the general tab, there's the set list down at the bottom, the set chooser, and you just click which arrows you want any particular component to be in which sets. So in this case, we have AVL, parasite, airspace, and battery as sets that we've named. And this front wing is in 3 out of the 4 of those. And so geoms can be members of more than one set. The geom browser itself, which has some of these really commonly used functions like show, cut, copy, paste, and controlling the visualization like hidden shade and texture, sets are important enough to have made it right here. Down at the bottom, there's an area for working with sets. You choose which one, and it'll show that list: AVL, parasite, battery, etc. And then you have these fundamental actions that can be done on sets. You can show only a set, you can show a set, no show, or select all of a particular set. In fact, under the hood, you don't need to know this, but show and no show are actually implemented as sets. They're special sets that we're constantly putting components into and out of to control that visualization. There's also the set editor, which you access from the model window. And so you click model set editor and it pulls up this window here on the right. And you can use this to change the name of a set. This is the only place to name a set. So you come in here and you name them. You can manipulate the membership by choosing then, if you say come to the parasite drag, and you can turn on which ones you want in parasite drag. There's some other manipulations. For example, you can add everything to a set, remove all. You can copy the members of one set and then paste it into another set. You can select a set from here. And then you can also choose when you copy a geom, you want to copy that set membership. And that's a behavior that we thought users may want it one way sometimes and the other way other times. So we make that an optional control here to control that behavior right from this GUI. Changing gears again, and really one slide is not enough to do justice for subsurfaces. But subsurfaces will also come up in some of the modeling. But what they allow you to do is demarc an area on the surface of another geom. So here's a pod, and here in UV coordinates, we've drawn a rectangle and an ellipse on that pod. And this subsurface, we've marked an area on a surface, and that can be used by different analysis tools for, say, for mass properties. You might, not our mass properties, but you can imagine different boundary conditions in an arrow tool. You could say have an actively cooled patch on a high-speed vehicle, so that you have part of it is actively cooled and other parts of it are passively cooled. So you're applying different boundary conditions to CFD. This is how we mark out control surfaces for deflections in VSP arrow. And you can also use them just as something visual. You can use them to draw windows and doors on your airplane by using subsurfaces for that. The subsurfaces are carried through to some of the modeling, some of the different analyses that we do. When you do comp geom, for example, it'll obey and it will split the triangles to mark what's in and out of each subsurface, so that you have tags that tell you where the pod itself is, where the rectangle is, where the ellipse is, and then notice even separately where the union of the ellipse and the rectangle are. In a similar manner, CFD mesh obeys those kinds of rules and will mark out and make a mesh that obeys subsurfaces. You can use them for all kinds of purposes, and they come in very, very handy. And with that, I'm going to fire up. I've only got just about 5 minutes for a quick demo. So I will try and just show a couple of quick models. First, I will, and if there's any questions, Brandon, you can ask them to me verbally while I open this up.
Yeah, we had a quick question that said, are child components automatically added to the set that a parent belongs to?
They're not. Right now, when you add a component, there's it's not a member of any set except for shown. So here's that compound fold model that I talked about earlier. First, we'll look at the fold out here at the tip. You'll notice that It shows the rotation axis, so we're rotating about this red axis, the X, and the X-axis goes right down the top of this wing surface. If we look at this fold hinge right here, and we look at its orientation, we're just using the X-form tab to locate it. And here we've actually translated it on UV. So we've placed it at U of 1. So that's all the way at the tip of this inboard wing section, and W of 0.5. That means all the way at the leading edge. So we've attached it right there. And notice we've attached it differently. We've attached it in UW in translations, but the component in rotation. So that's why it's still straight and aligned that way. Then we've bumped it up in the Z. We've incremented it in the Z half the thickness of this airfoil, so that we came up that 0.125 to get it lined up right there. And so we've got that perfectly aligned the way we want it. And if we come out here to motion, you'll see its limits are set to 0 and 180. And if we click that range, and as we fold it, we're rotating about that point, you'll notice the dashed lines, which are the moving side of the hinge, and it folds right over until it lays down on top. We want 180. Looks like we could actually go a few more degrees if we wanted to compactly tighten it, back it down. Now that we've folded that, we can take a look at our Grumman hinge. That's a little bit more obscured by the geometry, but notice we're again rotating about the red axis, which is oriented pointing, if we sight along it, 45 degrees in and down, which is the way a Grumman hinge works. We set this up. Its attachment point it's attached again in UW to the parent, to this inboard section relative to the leading edge. So notice its attachment point is right here. And then what we've done is we've translated an X, so we've moved it 0.75, which is down to the quarter chord. And then we've rotated 45 minus 45 to do that in and down rotation, so that we actually use the X-form type rotation for both of these. We didn't use any of the more advanced. And so then when we want to move this, we've already set our limits, our min and our max, to minus 141. If we click that range, but so now as we rotate back, we're rotating about that axis. This isn't the best view. Let me say look from the front and down a little bit, say about there. As we rotate it, that tip droops down, folds back parallel, and in this case, we've folded it back along, and we've got a lot of sweep. That's why it looks a little bit different than you might be familiar, but we folded it back parallel to the body and along the aircraft. So that's using hinges and attachments in this model. While we're here, let me open a different model that shows some use of sets. This is I'm opening one of the models that Uber has released of some of the concept vehicles from a couple of years ago. This is the ECR M3. Let me shade all of it, and I just chose it because it's a model that had sets used from the start. So here you can see we have AVL, parasite, airspace, and battery. So if we want to look at the AVL, we can show only those components. And these are then the components that you would then send in a model to AVL. Whereas for the parasite drag, these are the components that are in the parasite drag model. And the airspace model adds the propeller, the propulsion components, and the battery model just has the batteries only. So we've used these sets to group, again, to group by purpose, by function, what we're going to use these for, and then we use that to feed to different models. And with that, I'll wrap up this particular talk.
All right. Well, thanks a lot, Rob.